All right. Thank you very much. Thank you guys for coming. Thanks for having me. Hi. It's been a while since I've been here at NWCPP. Last time I was here, I was talking about ranges. Was anybody actually here for that talk? If okay, yeah. Just to refresh some people's memories, I talked about an application that I developed an application using ranges and range adapters and pipelines and actions and all that other stuff, and painted this really beautiful picture about what programming was going to be like in the future. And now I'm here to talk about the ranges TS, which incidentally doesn't have pipelines or adapters or actions. So what am I actually going to be talking about? Well, it has plenty. In fact, I have plenty to talk about tonight. I didn't have time to make this a short talk. So if I'm still talking at 8:30, just shoot me. Okay. So I'll be talking a little bit about what is actually in the ranges TS, which is going to be finished real soon now. And I'm also going to be taking a look at a little bit of the stuff coming down the pipe, so to speak, with regards to coroutines and how that intersects with ranges. So hopefully we can get to that before somebody shoots me. Oh, there. Okay. What's in the ranges TS? We have a bunch of concepts. The ranges TS is based on the concepts TS, which was finalized about 2-3 years ago. And so in the concepts, we have concepts like default constructible and regular. We have iterator concepts. That's the things that we know already and love, like input iterator, forward iterator, but we have concept definitions, so you can constrain your algorithms using these concepts. We have callable concepts and range concepts. We also have some concrete iterator types, like a better move iterator, something called common iterator, some counted iterators. So you could say, like, okay, I'm going to have the next this iterator and the next 5 elements. You could build a counted iterator out of it. And we've got a bunch of algorithms that are going to be constrained with concepts. And we have overloads for iterators and overloads for ranges. That's, in one slide, what is coming in the ranges TS. And also I'm going to be looking at this guy over here, Casey, because he's a co-author of me on the ranges TS, and he'll correct me if I say anything wrong or stupid or inaccurate or otherwise lead you astray. Okay, what's not yet in the ranges TS? As I said before, the really good stuff, the exciting stuff, is unfortunately not yet in the ranges TS. So the views, which are the non-mutating algorithms, and the actions, which are the eagerly evaluating mutating algorithms. Why are they not in the ranges TS? Because it was just a huge amount of work. And the ranges TS, as it is, stripped down to its bare minimum, is the largest TS that has ever been. And I have this on word of the guy who's doing the documentation for cppreference.com for the ranges TS. He's like, there are more entries for the ranges TS than for any of the other TSs. This thing is ginormous. But if you want to see me talk about all of this stuff and the sort of programming that they make possible, that ranges talk that I gave here at NWCPP, I also gave at CPPCon, I think in 2015, and you can catch that here. I'm going to be uploading these slides so you'll be able to download all the slides from nwcpp.org. I might need to move my computer so where this clicker works. All right, let's try that. Oh, that's better. Okay, so where are we in standardization. Way back in November of 2014, I had this idea that C++ standard should have range support in it. And so I presented a position paper, which wasn't a standard document per se. It wasn't like, didn't have wording in it or anything. No concrete proposal, just like, I think there should be ranges in the standard. Here's kind of what I think it should look like. If you're curious about that, because it gives a very high level view of the design and the rationale, you can find it there. It's still quite accurate. The first draft of the TS to be, I was done with that in May 2015. That's the meeting that this guy Casey showed up to with my paper printed out in a 3-ring binder, gone over with a red marker, and I was like, who is this guy? This guy's crazy. He should work with me. And then many, many revisions later, ISAQA, the range's technical specification, was called PDTS, which means preliminary draft technical specification, which is like, almost a technical specification. It's kind of like, it was canonized. And here, I think in July of 2017, all things willing, we'll have a final document. Oops. All right. Back. Forward. Okay. So if you're interested in the latest draft, here's where you can find it. Published March 15th of this year. And this is the link, the N4651. And that'll take you right to the latest draft, and you can find all of the nitty-gritty. It's about 200 pages of dense standardese. Last I counted. All right. Okay, so when will my vendor start shipping an implementation? This is like the $1 million question, right? So I have no idea. I do know that we've been talking with the GCC guys who want to ship our reference implementation. Don't know how far along they are in that process. But if you actually want to play with something today, you can grab my range library from GitHub, which has all of this stuff and then a ton more, including the views and the actions, all the things that will be proposed for standardization eventually, but aren't yet. Or you could use Casey's reference implementation, which is also on GitHub. And this is, this is, like I said, C++ 11 is my code. This is for a compiler that implements concepts, the concepts technical specification, which basically means a recent version of GCC with a special compiler flag. That's what you need in order to play around with the real thing, which is this. This is probably what's going to end up shipping in GCC. Or if you're on a Microsoft compiler, there's an extremely out-of-date port of my Range v3 library to Visual Studio 2015. And I might have to stop using this. Send complaints and bug reports to Microsoft, please. Yeah. All right. So here's the philosophy in one slide of the Range's technical specification. Sorry, Andre. He gave a famous talk that in D, ranges should be the basis operations. Everything should work with just ranges, and iterators were for the birds. This is not the philosophy that we take in the Range's technical specification in C++. And there's lots and lots of reasons for why we decided not to go that direction for C++, and here's a few of them. In the Range's technical specification, we keep iterators, and ranges are an abstraction over them. We, I don't know, the royal we, I guess, think position is fundamental. Iterators denote position, and it's very handy to have a notion of position in your standard libraries, algorithms may want to return positions, for instance. And operations on iterators form a more powerful basis. I've spoken with Andre about this. He actually agrees that iterators, although they are a more complex abstraction than ranges, they let you do more things, and they let you do more things more efficiently. So for C++, we think iterators are a winning abstraction for that reason. And also, look, we've been dealing with iterators in C++ for so many years, we couldn't really switch horses now. We're just too invested in the iterator abstraction to consider pitching it and dealing solely with range-based interfaces. And also, and this is partly addressed by the ranges TS, not entirely, we'll be able to hide a lot of the extra complexity of iterators behind library interfaces that make it appear like you're dealing solely with ranges. So that's basically why C++ is taking a different tact than Andre and Walter did with the D programming language, the standard library. Ranges, we have a concept hierarchy in ranges. We have this sort of, the range concept is basically anything that provides a begin method and an end method, and as long as begin returns an iterator and end returns something that can tell you when you've reached the end by comparison with an iterator, then that's good. You're a range. There are some refinements of range. There's like container. We all know what a container is. It contains elements, right? The idea of a container like that contains its elements is when you copy a container, it copies all of the elements. And that's different than, say, a view, which is also a range, but when you copy the view, you're not copying the elements. It has order 1 copy. Both container and view have begin and end, and you can pass either one to an algorithm that expects a range. The algorithm wouldn't care. But if you're dealing with it in your generic code, you got to be aware of when you're dealing with a container, because these things are expensive and heavyweight, as opposed to when you're dealing with views. We also have this extra refinement called sized range. This is handy to make your generic code more efficient in a lot of ways. You can ask a sized range what its size is, and it'll tell you in order 1. So this is what's actually in the range's technical specification, header-wise. So if you clone Casey's Git implementation, and you compile with recent GCC and the F concepts flag, then you can pound include all of this stuff, and you can have access to what's in the ranges TS today. So.
Does that replace the algorithm, or does it work with the existing algorithm?
Right. So this doesn't. This is purely additive. So all of these headers are going to define entities that are in stood experimental ranges, the stood experimental ranges namespace, right? So these have nothing at all to do with the stood algorithms. These are new algorithms in a totally different namespace than the stood algorithms.
And when it becomes final, it's still not going to say experimental. What will that include be?
Right. So.
I mean, your best guess.
Right. So I think I should be repeating questions, yes, for the televised audience. So the question is, when it is final, will it still be experimental? There's 2 answers to that question. There is when the TS becomes final, yes, it will still be in the stood experimental namespace, because all TSs are experimental. When the technical specification, well, if and when the technical specification becomes part of the international standard, then we will do something different. And something different has yet to be determined, but what the committee has been talking about is that this is the basis of a wholly new standard library, which will be in a different namespace than namespace std, probably namespace std2. So this is the start of a new standard library. Yes, question?
So now that you have algorithm and all these other STL concepts, you're building this on top, how is modules, the implementation of modules going to affect this include functionality?
So the question is, what happens when we get modules, and how does it affect the range's technical specification? We've done no thinking at all about how ranges affect this. What I imagine we will do is we will have one module for the range's technical specification, and you could pound import experimental ranges. That's off the top of my head, but it seems to make sense to me. With modules, I am told it doesn't make sense to have fine-grained headers. You would only want to do fine-grained modules. Fine-grained modules would only make sense if parts were changing frequently. And we're not going to be revving the range's technical specification all that often, so you'd probably just want it all in one great big module. Yeah. Question?
Is there a plan, or do you have an idea of what might go into this new std2 library, or is that still up in the air?
So the question is, what's going to go into std2? Don't know yet. We're going to be opening it up. Once we have the ranges TS finalized, we start talking about how we're going to work it into the international standard. Then it's going to be a cattle call, and everyone is going to want to get their favorite thing into to the new namespace. What I think we're going to want is as much of what's currently in namespace std that makes sense to add concept checks to. So I'm imagining a lot of stuff that's in the containers. It'll make sense to add concept checks to the containers, to the things in functional, to a lot of the things in utility. So there's going to be a lot of mostly the same interfaces in a different namespace. And the reason why we would want the duplication is because adding concepts is progress, but it is progress that's not exactly backwards compatible. And we generally want to get to that, that fabulous, nirvana where all of our interfaces are constrained and concept checked. But we don't want to pay the price of breaking everyone's code in the world. So we'll eventually bite the bullet, we'll fork the standard library, and we'll use this as a starting point. Yeah. All right. So you've got code, and your vendor starts shipping the ranges TS, and you've got some decisions. How do I migrate my code to use the ranges TS? So let's imagine that you've got some code. You're sorting a vector. This is an easy one. You want to migrate to the ranges technical specification using this. Then you could just call ranges sort. You pass it the vector instead of passing begin and end. Well, we've wanted this for a really long time. With the ranges technical specification, this just works. So all std algorithms have range-based overloads that dispatch to the iterator-based overloads. And it does that just by calling vec.begin, vec.end, and doing the obvious thing, dispatching. Simple enough. So say you have some code that's checking whether all elements in a range are valid by, you've got a vector of data. Data has a valid member. You're calling std all of, and you want to see that, all of the elements in your vector are valid. Right? What would this look like with the ranges technical specification? You could say all of my vector, and here you can take the address of the data member, and you could pass this as a callable thing. All right? It's taking the place of this lambda. The idea here is that pointers to members can be treated as callables of, say, in this case, it's a callable of one argument, right? And it saves an awful lot of typing. So any questions about that? And here's another example. You want to find an element with a certain property. You call find if with a lambda. Again, you can use invocables here. You can take the address of this data member, and you'd say find the range, the element, and then this is what we call a projection. That is, before I execute the algorithm, I want to project every element through a function. Right? And so what's going to happen is every pair in this range is going to get projected so that I'm going to be only looking at the first element of each pair. And from that sequence, I'm going to be looking for the value 42. So you'll notice that I went from find if, having to pass a lambda, to just calling find. I just want to find the value 42 using this sequence. Yeah, question?
And the second argument is intentionally the address of a type element.
So
that's kind of what the previous example was?
Yes, yeah, exactly. So I'm taking the address of a data member here, and I'm treating this as a callable thing. But you could pass any callable thing. In fact, if you wanted to pass a lambda that took a pair and returned the value of dot first.
Two elements.
Yeah. Sure, you could do that too. Any sort of projection that you could imagine, anything, any unary function. No. So you think projection is kind of a strange feature. Why did they add projections? So here's an example that I stole from a slide by Sean Parent. So projections, they increase interface symmetry. So here's one example where you have a bunch of employees, imagine this is employees, and you sort them by their last name, okay? And now what you want to do is I've got a sorted list of employees. I can look up employees very rapidly using lower bound, because that's what we do. We use lower bound, divide and conquer, search through sorted data sets. But the lambda that I pass to lower bound, I'm going to be comparing strings and employees, right? Because I'm searching for a last name in a bunch of employees. But when I was sorting, I had to pass a predicate that took 2 employees. So here, I have a lambda that's almost exactly like the lambda here, but the arguments are different. Do you see that? So it's real simple for these 2 lines of code to get out of sync. Right? You could easily imagine changing the lambda in one place and forgetting to change the lambda in the other place. And so now, if your sort and your lower bound are out of sync, then you've introduced a bug. Right? We can rewrite this with projections much more concisely. We could sort using just the standard old less, project the input sequence using the last name of the employee. All right, so I'm going to be just like up here. I'm sorting this range of employees on the employee last name. And here, I'm doing my search now, also using just less and projecting over the last name. So now these 2 lines of code are obviously in sync. So this is an argument in favor of projections because they make it possible for you to write code that is more obviously correct. That's kind of a subtle point. Are there any questions about that? Yeah.
Let's assume that we get a chance to provide the same lambda in the first case. Then in that case, we could preserve the lambda in some variable. And in that case, we would have only one place to change the code itself. Can all similar thing can be done in the second case? Because yes, we still have the similar code, but we still have a chance to miss change one line and forget to change another one.
Yes. So the question is, there's still potential for error here, right? If I accidentally projected on an employee first name when I was sorting and searched by employee last name. Same fix there. You would take the projection, you would assign it to a variable and use that variable name in both places, and then you wouldn't have that problem. Which you couldn't do without projections because these two lambdas would have different types. Yeah? So you couldn't assign them both to the same variable. Yeah. So there's actually another reason for why projections are useful in the range's technical specification. And it has to do with mathematical simplicity and correctness. So say I want to check whether or not a bunch of employees and a bunch of IDs are equal, right? In the STL, we could use the stood equal algorithm with a lambda that takes an employee and an integer and returns true if the employee ID equals that integer. And you do that for all of them, and you get true or false. If you do that in the range's technical specification, you actually get an error. And I'll explain why in just a little bit, but this is one of the things that we're going to need to watch out for as we're migrating code from the STL to the range's technical specification. If you just replace namespace stood with namespace range, there's going to be a couple of places, not very many, but a couple of places where you're not going to be able to do that without actually going in and making some small changes to your code. So why is that? Well, ranges equal is an algorithm that takes two ranges and a relation. Relation is the concept that's being used to constrain this binary function. And a relation is a mathematical thing. It has a mathematical definition. So it's basically a function of two arguments that establishes a fundamental relationship between these two things. So you could think of equality comparable is a relation. Strict totally ordered. Right? That's another relation. These are relations that are very important and fundamental to the standard template library. So relations are symmetric. If you can say a relationship between A and B, that same relationship had better hold between B and A. You know? And if you say there's a relationship between A and B, well then what exactly does that mean? If I say A and B are equal to each other, does that just mean I can find an operator overload that compares these things and returns bool? Or does it mean that they're actually equal, that I can use mathematical reasoning of substitutability to say my program is the same. If I replace this A with a B, then those two things are equal to each other, mathematically, right? Substitutability. So there should be some substitutability between A and B, even if they have different types. They should be representations of the same value fundamentally. So for instance, I could compare a char star and a stood string. Even though they have different types, they are fundamentally representing the same thing, right? In what sense, then, is an employee and an integer equality comparable? These things are not substitutable in my program. I can't just replace an integer with an employee or an employee with an integer and expect my program to behave reasonably, right? So how do I reason logically about my code and about the correctness of my code. So the way we kind of get at this in the ranges technical specification is we imagine that there's a concept called common type. So that in order for me to compare these things, for me to express a relationship between two things of different types, those two different types must share some common type to which these things can both be projected, right? So I can project a character, a null terminated character string into a stood string, right? And that doesn't change its value, its fundamental value as a sequence of characters. And then do the comparison that way. So this is what this line of code is saying, pseudocode, that if I can apply a relationship to an A and a B, that's roughly equivalent to, like, find the common type between A and B, project them both into that common type and do the relationship there, and that better mean the same thing. If it doesn't, then I can't reason mathematically about the correctness of my code. So if we back up, we can now kind of see why the ranges technical specification rejects this. Because this is not symmetric, right? I can't pass an integer here and an employee here. That's not the signature of this function. It doesn't work. And also, there's no common type that between employee and integer. These things are not substitutable. So you think, oh my God, this is going to be really hard to use. It's really strict. And the notion of strict type checking comes directly from the original proposals of these concepts, which was the Palo Alto report. A bunch of experts, after the C++ OX concepts debacle, got together and were like, we're going to start concepts over from scratch. And we're going to write concepts the correct way. And we are going to specify what all of the algorithms absolutely need in order for us to be able to prove mathematically that our programs are correct. And they said, these are strong requirements, but we feel they're justified. The additional requirements make it possible to reason about the semantics of cross-type relations. They make it possible to describe such relations as equivalence relations or strict weak orderings. We stuck to our guns. We adopted this design. We're going to see how it goes. So how do projections help? Because when I was talking about projections, so this is how it's done today in the STL. This is the simple, straightforward port that doesn't work. Here's how you would do it so that it does work. You project all of your employees using their ID. So before you apply your relation, before you apply your equal to relation, you turn all your employees into integers, and then you compare them as integers.
Why are you calling these projections both member data pointers?
Oh, so apologies. Yes, this is a member data pointer. It is basically treated as the ranges technical specification. It's just a unary function, right? This is a function that takes an employee and returns its ID. That's how it's treated by this algorithm. And I'm using the term projection here to mean just any unary function that is going to be transforming your input before you apply your relation.
It might have to be a mathematical operation or a multi-step function to do that.
So when I say projection, just think unary function. It's just a function that takes one argument. Yeah. Yeah.
And is there an overload of ranges equal that takes yet another argument, which is a pointer to a member function that operates, or a member function that operates on the second argument?
Yeah. Yes. So the question is can I also pass in a unary function that transforms this input before applying this relationship? And the answer is yes, you could pass another one after this. And it doesn't have to be a data member. It could be any function. I could pass a lambda here. I could pass any function that takes, this is paired with this. So whatever I pass here, better accept employees. Yeah. And whatever I pass, if I were to pass another one, it would be a function that took integers, because this is presumably a range of integers. Yes, question.
Conceptually, you're really describing the output type of your unary function, and the input to it would be the object and its type.
Yes. Yeah, right. So the observation.
So both can be converted to something totally unrelated to whatever the object is.
Right. So the observation is I could pass two functions here. One that takes an employee and returns a Baz, and another that takes an integer and returns a Baz. And then I can pass two Bazes to equal to and check them for equality. That works just fine. My system type checks. Everything's good. Yeah. Yes, question.
I mean, it's a little obvious, but the relation is to be like mathematical sound, like a function, same with projection.
Same with?
Same with the projection, but it's to work properly.
Right, right. So the observation is that the projection has to be mathematically sound too. And that's also correct. It's a lot easier for a projection to be mathematically sound. I don't even know how it couldn't be mathematically sound. Right? I mean, it can't return a random number. It has to be a regular function. That is, it has to be a function whose output solely depends on its input. Aside from that, you're good. Yeah. Oh, lots of questions. All the way in the back. Yeah.
Kind of get that for lower, but why not compose equal out of, like, say, ranges project, like having ranges project on employees with function and ranges project on IDs, and then pass them through.
I didn't catch the question.
So why not just projecting the ranges before passing them to equal, like in a lazy projection?
Oh, okay. So I see your question. So I could apply a transformation to employees directly, so make it appear like a vector of integers, or a range of integers, and then pass that to equal. You would achieve the exact same effect in this case. In this case, yes.
If you have a different algorithm, then the efficiency is a problem because you're algorithm my stuff, right?
So
You're evaluating the whole range.
let me think.
So if you transform the range beforehand, then you evaluate all the elements in the range.
Okay. So now I understand your point. So the question was, if you apply a transformation here, then you traverse the entire thing, do the transformation, and then pass the result. That's not actually how adapters work in the ranges the ranges world. In the ranges world, you can create smart iterators that apply a transformation as you iterate through the thing. So you don't actually have to walk through the entire set, transform them all, and then pass the result in. You could pass a result in that is going to do the transformation for you iteratively. But the reason why projections are here and useful now is because the ranges TS don't have those adapters. We didn't get around to specifying them. Projections are still useful in and of themselves, but once we have the lazy views, then you'll need them less. Yes, question?
I remember that the previous example you had with find, that would return the unprojected.
Yes, that is a very astute observation. So if you do actually, so if this were an algorithm that returns, say, an iterator, the found element, if this were find instead of equal, then the return type depends on the sequence type. And if you project this to integers, then you're going to get back an iterator that's pointing to an integer, when maybe you want an iterator that's pointing to an employee. Yes?
Is there a way of passing in another argument into your, I forget what we call it at the end.
This thing a projection?
Yeah, the projector, yeah.
It's a unary function. This is going to be a unary function. I don't know what other argument you'd pass in here.
I've got hashed information or encrypted information. I want to do a find, but I want to, as I'm doing my projection, to decrypt, look, and then throw it away. So I don't want to keep the unencrypted version anywhere. I need to pass in the encryption.
I I think it's fine as long as this is a regular function. As long as it accepts an employee and returns something, and every time you pass in the same value, it returns you the same result.
But it
That-
would need an extra argument of the encryption keys for all I'm getting at.
Could you find your lambda with capture? Or pass a lambda and capture whatever you do?
Yeah.
All right. I feel like we're getting a little far afield now. Yeah, let's get back to it. So this was kind of like the hardest slide. Now I think it's all downhill. All right. So sentinels. There's one other new thing that's coming in the ranges technical specification. In the STL that you guys know and love today, begin and end always have to return the same type. But that's not true in the ranges technical specification anymore. And I'd like to talk to a little bit about why. And to do that, we're going to look at a little bit of code, and we're going to look at generated assembly. So here's the example. We're going to write an iterator over a C-style null-terminated string. So right now, if you want to use any of the standard algorithms to operate on a null-terminated string, first you call strlen, right? You find the end of the string, you pass the begin and the end of the string. Okay, what if your string is potentially like gigabytes long and you don't want to have to probe for the end before you pass it to an algorithm, right? Maybe you're passing this thing to find, and it's going to find the result like 5 characters in. You don't want to have to walk over a gigabyte to find the end, just so that your algorithm can only walk over 5 characters and then it's done, right? You want to write an iterator that will find the end as it goes. So you pass like a sentinel end that will compare equal to an iterator when that iterator has found the null. It'll become clear as we look at some code. So this is an example of how to do it. Okay, so in this code, we have a cstr iter class, and it contains a char star that's initialized to null putter. And when it's initialized to null putter, this is the end iterator. Okay. If p is not null, then this is not the end iterator. Okay. Now all of these operators are really simple, like the dereference operator dereferences the string, the arrow operator just returns the pointer, incrementing the iterator just increments the pointer, right? And post increment is just a clever one-liner way of doing it once we have std exchange. The tricky bit is this guy here. So I have an iterator and another iterator, either one of which may be representing the end of the sequence, and either one of which may be not the end of the sequence, might be at the null or not at the null, and this equal sign has to handle all of those cases, right? So, you know, if I'm not the end iterator, then evaluate this or that. Otherwise, if I am the end iterator, evaluate this. Oof. This took me a long time to write, and I got it wrong like 3 times. This is not easy code to write. So, do you think this is going to generate good code or bad code? This is going to, right? Yes, Walter's like, this is going to generate terrible code. Absolutely right, but let's actually look at how bad it is. Let's compare it. This is like the basic like cstrlen, like just tell me the length of this string. And this is like cstrlen, but with our like smart C++-ish iterators, right? And this is the result, right? cstrlen is awesome, and our C++ iterator-based strlen is not awesome at all. Like, look at all of these, like, we got like tests, and we got jumps, and we got compares, and we've got like, it's all over the place. It's terrible. Yeah. Okay. So, let's change it up. In the ranges technical specification, you can use type information to help you by giving your end iterator a different type than the begin iterator. So here we have C** iter 2. This is like the ranges TS iterator. And it does all that other like boilerplatey sort of things, right? But when you're comparing it for equality, you can just compare pointers, right? If I'm comparing this thing to another iterator that I know is not the end iterator, I can just compare pointers, okay? And if I compare it to something called a sentinel, now I know at compile time I'm comparing something against the end iterator. I can check to see whether or not I'm at the null terminator, right? And we see how we use this. Now when I write my range strlen, I pass a C* iter 2 and a default sentinel. Now the type system is helping me here because when I do begin not equal to end, now I can dispatch exactly to the right code that needs to execute. Right. You think this is going to generate good code or bad code? It generates almost exactly the same code as for the C-style strlen. In fact, I think we have like one extra line. Oh, which is the extra line in here? There's an extra jump. We can jump straight to the end. Other than that, like here's our inner loop, and the inner loop is exactly the same as the inner loop that is generated for just raw pointers. So this is why in the ranges technical specification we allow the begin iterator to have a different type than the end sentinel. Just for performance reasons alone, it makes sense. But it also means that I didn't have to write this, and I won't have to write these sorts of awful iterator comparison for sentinel ranges anymore. Okay. So any questions about sentinels? Yeah.
Yeah. Could this be achieved if you just use the function that gets whatever begin returns as an argument and just returns true or false, so you can pull the result instead of the...
Can you say the question again?
Would we just use a function, end function, that gets whatever begin returns as an argument, that returns true or false?
Okay, I see. So, so the idea is that instead of doing this, range strlen with an iterator and a sentinel, and then comparing with this not equal, you could pass instead a done function and say done of begin. Is that the question? Right. So that was one of the directions we considered. The big drawback of a design like that is that it makes all of the existing iterator-based algorithms wrong. Because tons and tons of code is expecting something to be compared to something with equal or not equal. And as it is today, with the ranges algorithms, they work as they are whether you pass like begin and end with the same type, that is two vector iterators, or some like a vector and sentinel. And then the body of the function can be exactly the same. You just, you increment your iterator, you compare it to your end, right? And that all just works. And syntactically, the difference is totally papered over. So for pure backward compatibility and syntactic reasons, it's good to stick with the equal not equal syntax, even though it's kind of a strange way of calling a done function. But it is essentially what it's doing. Yeah. Question.
Can you say something real quick about how we changed the specification for range-based 4 to support the different types of begin and end?
Right. So in C++ 11 and 14, the range-based for loop, like the built-in language range-based for loop, expects begin and end to have the same type. In C++ 17, that has been loosened so that begin and end can have different types. And that was a proposal that I wrote because I saw this coming. And the committee agreed with me, and they made the change. So we'll actually probably get that change. That change is already shipping in, I think, a lot of the compilers, like all of the compilers?
The big three anyway.
The big three. So like Clang, Visual Studio, and GCC all allow begin and end to have different types now. Yeah?
If that's different types, does that also mean different types of alignment, like 64-bit versus 32-bit types?
So this has nothing to do with alignment.
Okay.
This is just different types.
So int versus float, or?
So, well, I mean, this for the range-based for loop, begin has to return an iterator, something that you could dereference and increment. Yeah, and the only thing that end has to return is something that you can compare to begin with equal and not equal. That's it. It's the only requirement on end. Whereas before it was required to be an iterator, which made no sense because you never incremented it or dereferenced it. You couldn't.
Okay, so it was an iterator type versus a...
Yeah, yeah.
So then would you need the operator that allowed you to compare the iterator to the type of the end as having been defined? Otherwise, how does it know that string pointer is supposed to match the end, which is a null character?
Right. So absolutely, this operator has to be defined somewhere, and the compiler is going to use argument-dependent lookup, as it always does with operators, to find the overloaded operator that matches, and if it doesn't, it's a compiler error. Yeah. Okay. I think that's all I really wanted to say about sentinels. Yeah, we give the optimizer more context, resulting in better code gen, and then iterators become easier to write correctly. All right. So we looked at how to migrate your code to use the ranges technical specification. What if you have your own algorithms and you want to sprinkle them with the rangy goodness? This is this part of the talk is going to be pretty quick, I think. Say you have your own insertion sort, and like good STL algorithm, it operates on iterators first and last. Who's seen this implementation of insertion sort before? This is like such a gem. I love this. I think I got this from Sean Parent because it has rotate in it. So you want to migrate this to use the same interface idioms that ranges technical specification does. So the first thing you'd do is you'd switch the std algorithm calls to the ranges algorithm calls, because they're properly constrained with concepts, and if you use them incorrectly, you'll get an error message telling you that you're using them incorrectly, and how, presumably. So that's easy, no-brainer. The next thing you'd want to do is you'd want to properly constrain your own algorithm. And you can use the concepts that are defined in the ranges technical specification for this. Notice that before you had type name I up there, template type name I. Now you could say template forward iterator I. Forward iterator is a concept that's defined in the ranges TS, and you can constrain your algorithm by specifying that this template parameter had better satisfy the forward iterator concept. All right. We just finished talking about sentinels. You should be able to accept a sentinel here too. Instead of taking an iterator pair, you could take an iterator sentinel pair. And so that's how you constrain it. You'd say forward iterator I, sentinel of I, type S. I first, S last. Simple enough. And now, since we're taking a sentinel, we might not actually know before we call this algorithm where the actual end of the input sequence is, right? Because think of like passing our C string iterator. When we created the C string iterator, we knew where the start of the string was, but we didn't know where the null terminator was. As a result of executing this algorithm, you're going to discover where the location of that null terminator is. And that's useful information that you'd want to return, right? So with the algorithms in the ranges technical specifications, a lot of the return types of the algorithms are slightly different. They return a little bit more information. So in this case, we'd want to return the actual position of the end iterator when the algorithm is done, because we don't want to throw away useful information. And then we just want to add an overload that takes a range and just dispatch to our iterator-based one. And just like the iterator-based one, we'd want to constrain it on with concepts. So any questions about that? I know that went by pretty quick. Does it make sense? Yeah? Oh, safe iterator? See, I knew I was going to get a question about that. Safe iterator. So you'll notice here that we're taking an R-value reference to a range. This could be an R-value reference. This is like a perfect forwarding reference, right? That could be an L value or an R value. You know, I can call this function with a L value stood vector, right? A named stood vector. And you'd want that to return the iterator, right? But if I were to pass an R value stood vector, I'm going to insertion sort a temporary vector that's then going to go away after this function returns. Well, I don't want to return an iterator to a vector that doesn't exist anymore, right? So instead, what the ranges technical specification does is for R values, it's going to wrap your iterator in a struct called dangling. So if you really want a dangling iterator, you can access the iterator stored within the dangling struct. Say like, I know what I'm doing. This isn't really dangling, trust me. It's C++, right? But the idea of the dangling struct is that it's probably not what you want, and we don't want to make it too easy for you to shoot yourself in the foot. So safe iterator is if R is an L value, you get the iterator. If R is an R value, you get the iterator wrapped in dangling. That's it. Yeah, question?
What about exception handling inside the range?
What about exception handling inside the range? This is totally, has nothing to do, it's agnostic about exceptions. It's entirely possible that, you pass it an iterator that throws an exception when you dereference it. That's up to you, right? The exception will bubble through this code, and this code doesn't care.
Would it use it back? Would it cause your program to terminate, or would it just...
No, it doesn't cause your program to terminate. The exception bubbles out of this call, and either you're handling that exception somewhere or you're not, and that's your problem. It's not a problem in this code. Yeah. Okay. All right. So that's pretty much what's coming in the ranges technical specification. I wanted to spend a little bit of time talking about some thoughts that I've had about future directions. So certainly there's the views and the actions. That's all very interesting stuff. You can go see another talk about that. But I wanted to present some thoughts about coroutines, because I think coroutines and ranges meet in a very interesting place. And I've only just started thinking about this, and I think it's pretty exciting. So who knows that coroutines are coming to C++? So most of you, great. This is an exciting development for C++, I think. So lightweight cooperative multitasking in C++. The coroutines technical specification. It was just declared PDTS, just like the range is TS. So it's a preliminary draft technical specification, which means that it's very nearly done. And having it very nearly done this early in the cycle for the next international standard means that it seems like it's plausible for C++20. But don't hold me to that. So, if you download my range v3 library, and if you grab some code from this guy named Toby Alsop, you can write stuff like this. You can generate an infinite sequence of integers using a simple for loop and co-yield, right? And it'll return a generator of integers. So loop over all the integers, yield each one, and return a generator. And what can you do with that? You can pass that infinite list of integers. You can say, take the first 10 elements, and you can print them. Now, what co-yield is doing is, right, this is a function that is a coroutine. And every time you yield a value, it suspends that coroutine as it remembers all the values of its local state and returns the value. And then the next time you call into this function, it'll pick up where it left off. So you yield all the integers in turn, and when you return a generator, it presents a range interface on that data, which you can then process with all of the range adapters, all the range algorithms, and all of the range actions. So I think this is super exciting. This is going to make writing your own custom ranges trivial. I think coroutines and ranges are kind of, yeah. Yes, question?
Bar and the take 10, is there any connection between the 10 and the fact that it's an I, or is it just has to be 10 numbers?
So no, there's no connection here between this value and anything that's going on up here. You could say take 100, you could say take 1,000, whatever you want.
But what I'm saying, but it's not connected to the I. So it's take the next 10 things, but the things could be people's names.
Yes, right. So it doesn't matter whether this is integers. I see what you're saying. Yeah. So it doesn't matter if your sequence is people or integers or strings or whatever. Just take 10 of them. Yeah.
This is what I thought.
Yeah. Yeah. Question?
Inside the sequence function, once the take 10 is exhausted.
So what happens to this coroutine when this statement is done executing? So the generator is going to be holding what's called a coroutine handle. So behind the scenes, what happens? And this is all very, like, my understanding of this is tenuous, okay? This holds a coroutine handle. The compiler will allocate a coroutine object and will pass a coroutine handle to it, to the generator. And when that generator goes out of scope, that is, at this semicolon, that generator dies. That coroutine handle lets go of the coroutine and it goes away. It's basically like a shared putter.
Once the information takes 10 elements, we can say that, the next function that will not be called anymore on the routine.
Right, so the generator has iterators, and you are going to be incrementing that iterator 10 times and dereferencing it 10 times to get your 10 elements out of it. And then when the generator goes away, that iterator becomes invalid, and the coroutine gets cleaned up. Yeah, question?
You could declare an infinite sequence on the stack as a variable and then call it multiple times in multiple for eaches and have it last longer than just that sequence?
So the question is, could I say, call infinite sequence, assign it to a local variable, and then iterate over the infinite sequence multiple times?
You wouldn't do multiple take tens on it. So you did, 10, 20, 30.
Oh, and then, yes.
So basically, it maintains state beyond each for each.
Right, so it would maintain state between multiple for each statements, in my understanding, yes. So if you say, take 10, then you'll get the first 10. If you do it again, you'll get the next 10, until that generator goes out of scope and it's all cleaned up.
And is that what it's not using that handle mechanism you're talking about anymore?
Well, it is. It is using the handle mechanism because it's the generator object itself that's holding the handle that is keeping the coroutine alive, and the coroutine is where that state is maintained.
Okay, so the variable.
What about multi-thread instances where multiple threads are potentially accessing the same variable of your instance?
Right, this is not thread safe, right? This coroutine object has to be local to your thread. Yeah. It's basically, yeah, you can think of it as fibers.
Why co-yield versus yield?
Ah, that's a good question. Because they, they wanted yield, but they were afraid they'd break too much code if they took yield as a keyword. Yeah. Legacy. Yeah.
Isn't that what underscore sort?
Underscore yield? I don't know. I don't know if underscore yield would be better or worse than co-yield.
Well, underscore is reserved for the language.
Yes, it is.
Single underscore, a lot of people use it.
Yeah, yeah, yeah. So I'm super excited about this. I think it's going to make things a lot simpler.
And the vertical bar?
Oh, this is an operator that is overloaded by the range v3 library, and it basically just means chain operations. It's kind of like the Unix pipe. Take this thing, pipe its output to this thing, and then pipe it onward to other things.
Take is really just a call an iterator of the iterator of the generator.
Yeah, yeah. So let's write filter. Filter is a kind of interesting adapter, right? I'm going to take in a range, and I'm going to skip all the elements that don't satisfy a certain predicate. Right? With coroutines, it's absolutely trivial to write this, You could just write a for loop for it, right? You've got a function, let's call it filter co, that takes a range and a predicate, and I can constrain it with some concepts. That's great and goodness, right? And I return the generator over the value type of that range. And the code is pretty trivial. For each element in the range, if it satisfies the predicate, yield it. That's it. I've just written filter, the filter adapter. Yeah, Walter.
Can you have more than one co-yield in the function?
Can you have more than one co-yield in the function? Yes, you can have as many as you want. Yeah. Question?
You specified the return type exclusively. Can it be, decided based on the type deduction?
So can the return type be deduced by the compiler? In this case, no, it can't, because there's lots of different things that could be generated as a result of a yield. Basically, how best to explain this? Yeah, Casey, give it a shot.
Co-yield needs to be there for the compiler to know that's a coroutine and not just any other kind of function code.
Yes. So Casey's point is co-yield just tells the compiler that this is a coroutine. It doesn't tell the compiler what the return type of the function should be. So you can write any sort of wrapper that you want that contains the coroutine handle. And it can present any sort of interface that you want, right? As long as it satisfies a certain awaitable concept so that when you yield, right, the compiler knows how to do the transformation. But you are free to write any old generator that you see fit. This is not anything magic in the compiler. Yeah, Walter.
Regular return statements mixed in there too?
Can you have regular return statements mixed in too? That's a good question, and I don't know the answer to that. I'm guessing that would be really confusing for the compiler. I don't even know what that would mean. Yeah.
Co-return.
There's co-return. Yes, co-return is different, but I mean that's also a coroutine operation. So, but the question is, can you just return, like a simple return statement in a coroutine? I don't know what that means.
Most likely this return will never get a control. So most likely we can return the function. This return will never be.
Yeah.
Will never get a.
I'm guessing it wouldn't compile. I haven't tried it though.
Yeah, it will compile with certain versions
Oh.
of Visual C, but we changed that.
Oh, okay. Yes, Casey.
Return cannot appear in coroutine.
Ah, thank you, Mr. Standard. Okay. You're checking the coroutines technical specification?
Yes.
Yeah, on your phone? Oh my.
I feel bad that I don't know.
Yeah. Okay.
Fix that when they compile.
Yeah. So I don't know about you, but I'm really happy at how simple this is. Because in my Range v3 library, the filter adapter is, I don't know, like dozens and dozens of lines of code. And I would love to replace it.
The code is simple, but the template
Oh, yeah.
function is complex.
Yes. The type signature is way more complex than the function itself. Yeah. And that's, yeah.
It speaks to it being a generic
Yeah.
filter, not specific.
Yeah, you know, and function signatures in the STL would be kind of ugly too if they actually bothered to say what their requirements were, which they don't. Yeah, question.
Yeah, I believe that you could not use concepts here and it would look a lot simpler.
Right. If I didn't constrain this function, it would look a lot simpler, but it would be less pleasant to use. So now we can filter our infinite sequence and only look at the even numbers, if that's what we wanted. And now what if you actually wanted the pipe syntax, if you were using Range v3? This is how you would get that. You know what? I'm not even going to bother explaining this. But it's not that hard. Okay. So then you'll notice something interesting about these generators is that although they appear to use some asynchrony, there is nothing actually asynchronous about them, right? I move the iterator to the next element, I march this algorithm forward one step, and I get a value. I mean, that's basically how we program. It's imperative, it's not asynchronous. The coroutines technical specification actually dips its toe into this notion of asynchronous ranges. Because there's this weird thing called for co-await. And this is an asynchronous for loop over asynchronous data. And here's what it transforms into. So imagine you have a range, and you can call begin on it, and that has to be something that you can co-await. Like maybe it returns a future of an iterator or something. And then range's end is not anything awaitable. And then you have your regular for loop, except moving to the next element is also something you co-await. So that is also an asynchronous operation. And this is how that for co-await transforms. The idea here is that you can asynchronously fetch the first element of a range and asynchronously fetch the next element of the range. That is, all the elements in your range are getting them can be an asynchronous event, something that you can await on. So you imagine your ranges are over network packets. And you can await on the arrival of the next network packet. Or maybe they are user interface actions, like the user moved their mouse, or they hit a key or something like that. An asynchronous range of something, right? You can for co-await and make your code asynchronous but appear iterative. What's that? Yeah, question.
Shouldn't be the reference of the begin fields asynchronous?
So the question was, shouldn't dereferencing also be asynchronous? It seems to me that it could either be incrementing or dereferencing. I think it makes more sense that it's incrementing, like move to the next element. But then I might want to access that element repeatedly, right? I could deref, keep accessing the same element, right? And I shouldn't have to await on that each and every time. If the element is already here, I should just be able to access it.
If you have a heavy operation, better to make it inside the incremental operation.
Yeah, for the heavy operation, you want it on your increment as you move to the next element in your range. Yeah.
It's physically possible. I would much rather see the await on the type, not, so it would be on the right, not the left.
So you'd rather see co-await over here?
No.
What?
Auto begin.
Oh, I see what you're saying.
Begin.
Yeah.
Wait for object.
So
Transparent when you're using it later. You wouldn't have to say it later. You could have just done the plus begin, and it would have known it had to wait.
So the way it works, as far as I am understanding in C++, is that expressions are awaitable. So I evaluate an expression, and either it returns something that I can await, or it doesn't. Yeah.
That would be the evaluation of the expression waitable. So
Yes.
The variable itself would have been
Right.
waitable, but then when you go to evaluate that expression, then it becomes waitable.
Exactly, right? So I could have just assigned ranges begin directly to begin, and then whenever I used begin, I would have to co-await on it. Yeah.
I like that.
Yeah. Okay. So this kind of got me thinking, like, there is a whole range library here that can be built around this abstraction, right? So hidden somewhere in here is this idea of a asynchronous range. There is a concept buried in here. So let's extract that concept. Let's imagine we have an await resume function. So I kind of like peeked into the ranges technical specification, and this is some magic that, you know, if Gore, the author of the proposal, were here, he could explain all of this to you. So await resume, so say you have, say, a future of int. When I say await resume on that future, it's going to return me the int in that future. Okay. So let's define an asynchronous input iterator concept. So it's readable, right? I can dereference it and get a value. It's semi-regular. I should be able to copy this thing around. And I should be able to await resume the increment operator of that iterator, right? And it better return me an I reference, right? Just like iterators today, when I increment them, they return, you know, a reference to themselves. And they might have a post-increment operator too. I don't really care. So this is the concept, in the language of the concepts technical specification, of an asynchronous iterator. And this is the concept definition for an asynchronous input range, where I can await resume the begin, right? So this thing is an asynchronous input iterator. And it should have an end iterator that is weakly incrementable, right, to the awaited begin. I know, this is like, you've probably seen nothing at all like this before, and it might look like gobbledygook. But in the language of the ranges technical specification, this is how we say in code the requirements of this. Yes. Okay. So what can we do with that? Let's imagine we start building a standard template library for asynchronous ranges. We can have asynchronous algorithms, right? Notice that I'm taking asynchronous input iterators here instead of input iterator, And here's what an asynchronous find algorithm could look like, right? I could co-await on the iterator. I can execute my algorithm, searching for the element, and then I can co-return the found iterator. So this is a completely asynchronous find algorithm, so that I would be able to co-await the result of calling find on an asynchronous range. Yes, question?
Does the range have to be constant, or can it be still accepting values into that?
It couldn't be constant.
So does the range have to be constant? No, I mean, what do you mean by constant?
Constant size, that we're not changing the container that we're looking at.
This doesn't care about the size, like how many elements are going to be in this asynchronous range. It could actually be infinite.
Right, but I'm just saying that when I think of asynchronous, I'm thinking that it can always be updated.
Right, it's reading from a network.
Yeah, it could be reading from a network, like totally asynchronous.
So therefore,
Yeah,
the
unbounded.
values are changing while we're trying to iterate. That's
Yeah, it's data driven. Yep, data driven.
That's why you have the sentinel rather than actual value.
Yeah, yeah. Question?
What happens if it's not found?
Well, this,
I equals last, or finally.
if it's not,
What are you returning for the other?
then you return the end iterator position. Like eventually,
It's a different type. There is no end iterator.
well, no, actually, you're not returning last. You're returning I. I starts at first and is incremented through and becomes equal to last. It never changes its type. And then you return it. You co-return it. Works. I tried it.
And you
Yeah.
could use a code yield on that, like you do repeatedly.
Could you use a co-yield here? I'm not exactly sure what the difference between co-yield and co-return is,
Well, I think
to be honest.
forcibly destroy.
Co-return. Right, exactly. That's exactly right. Co-return is going to destroy your coroutine because you're done with it. Yeah, but co-yield suspends it so that you can resume it. Yeah, that's correct. Okay, so the idea here is that we've got this abstraction. We can build generic components around this abstraction and program generically with asynchronous data in the same style that we would use our synchronous data. We would also have like a find that takes an asynchronous range and is implemented in the obvious way. And now we can define asynchronous views over asynchronous ranges. So we can define, like we showed, like the filter. We can have an asynchronous filter view that is awaitable. Its input would be an asynchronous range. We can do asynchronous transform, anything that accepts input iterators, not forward iterators, because you can't save off a coroutine and restore it later. But anything that operates on input iterators, we can create algorithms and views, not actions, algorithms and views that are completely asynchronous. And now we can filter and transform infinite asynchronous sequences of network packets, of user interface events, file system notifications, or whatever. And we can make our programs completely data-driven using this abstraction, which I think is pretty exciting, which gets us to reactive programming. And that's pretty much where reactive programming, that's the essence of reactive programming. We have asynchronous lists of events, and we program in a way that lets our programs be driven by the data as it comes in. So, coroutines make it trivial to define lazily evaluated views of data sequences, and the ranges TS gives us the algorithms that make operating on those views simple, and they could also be asynchronous, and with algorithms and views that are async aware, we can write generic code that's either imperative or reactive depending on the type of the input, which which I think is pretty exciting. It's a new, cool direction. I'm looking forward to digging into that. Yeah, questions?
Question about sentinels. In the current implementation of iterators, for example, if you are trying to dereference the end iterator, so that like an iterator itself has a chance to check whether it's in an end position or not.
Mm-hmm.
But with the sentinels, for example, in the example with the asynchronous range,
Mm-hmm.
if you return some iterator that points that it's equal to n, and for example, the developer, well, forgot to check whether it's n or not, and dereferenced it, the potential is get garbage in this case, or some seg fault in a worst case.
Seg fault if you're lucky.
Yeah.
Garbage if you're unlucky. Yeah.
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 Isn't it a way to write more dangerous code accidentally?
So with Sentinels, can you write more dangerous code accidentally? I'm not sure you can. Certainly, in one sense, the world is a better place with Sentinels because your code that tries to dereference a Sentinel isn't even going to compile.
Yeah, but if you're trying to dereference the Sentinel, but if you're trying to dereference the iterator, and well, with Sentinels we detach iterator from the end.
Mm-hmm.
So iterator itself doesn't have any information about the stop.
Yeah.
The stop sign.
I mean, this is a problem with iterator-based designs, regardless of whether Sentinels are there or not. And I don't think Sentinels change it. Walter will tell you that range-based interfaces don't suffer from this problem because there aren't iterators. Either a range has elements in it or it doesn't, and that's easy to tell. You just ask the range whether it's empty or not. And if you are programming with, at the range interface level, then you can't get yourself into this problem because there isn't a notion of a dereferenceable range. Well, ranges aren't dereferenceable, right? And it's always easy to ask the range whether it's empty or not. Once you drop down to the level of iterators, this problem creeps in. You have the potential for invalid iterators. You have the potential for iterators that are not dereferenceable, if they're equal to the end iterator or end sentinel. And so that's just the state of the art with iterator-based designs. That's all I've got. Sorry. Yeah, question.
Speaking of which, I don't know if you showed an example when you have iterators like based algorithms, you say find, for example, right? You get an iterator back and you compare it against the end iterator that you passed there. For ranges, are you supposed to compare it against the end of the range?
Right, so the question is, if you've got like the find algorithm that you pass it an iterator and a sentinel, and it's going to return an iterator, and you want to find out whether the element was found or not, what do you compare it against? You would compare it against the same sentinel that you passed into the algorithm.
But if you pass it in a range, there's no sentinel, right?
Right, if you passed in a range, then there's no sentinel. Then you would compare it to the end of the range. Yeah. Which is why for something like find, you might want there to be an algorithm like contains that returns bool, yes or no. But if you care about the found position, then yes, you'll get back the iterator. And if you want to find out whether it was found, you can compare it to the end of the range.
So why actually have and if you would always have to use the sentinel? Want to make and out of the sentinel. The implementation of sentinel in the end, in the ranges, why make them two separate types?
I'm not sure I understood the question.
Well, begin is a specific implementation, and depends on your iterator.
Mm-hmm.
But it's normally just like a checking for null or something like that. Why not, in ranges, just make and, rather than actually predetermining where the end is, why not just make it internally how you've done sentinels?
Okay, so the question is like, why have end at all? Why not just have sentinels? Or just...
Why even bother with sentinels? Why not make your implementation at the end use sentinels, or be the sentinel?
So why not make end just return the default sentinel like I showed it on that one slide? Was that it? Okay. So the answer is that for a lot of ranges that doesn't make sense. A good example would be vector. Vector knows exactly where its end is and would want to return an iterator, not a sentinel, for its end. Yeah. So you could like decrement the end iterator. Right? You couldn't decrement a sentinel because a sentinel doesn't know its physical location. A vector iterator does. You can get the end of a vector and decrement it and get the last element in your vector that way. And that's a useful operation. Yeah. So for some ranges, it makes sense to actually have end return an iterator as opposed to a sentinel. Yeah, question?
So the last part of the presentation was very interesting, the whole presentation. It's very exciting to see this combination between these synchronous coroutines and synchronous ranges. And I was curious, so it looks like we start exploring that combination of these two. And since composable and also the coroutines seem to be in a pretty advanced state, I was wondering if you worried that you're going to discover some compatibility kind of late and then say, oh shoot, I should have discovered this before.
Right, so the observation was that, okay, like coroutines, this looks like interesting stuff. Ranges, this looks like interesting stuff. There's definitely some sort of interesting overlap that maybe you guys are only starting to investigate now. What if you guys discover a problem? And that's exactly what technical specifications are about. It's about discovering problems. So this is exactly the time, now that we're getting implementations of these things, and we can start actually playing around with them, that we're going to start discovering problems that we could address and have time to address before we bake all this stuff into an international standard. So this is exactly the right time to be doing investigations like this.
And if you publish first, you're the right one.
Yeah. Yeah. All right, any other questions? Yeah, one last question.
What would happen with range namespace once the documentation becomes standard? Will it be ranges namespace, or will it be merged into the student namespace?
So the question is, what becomes of the ranges namespace? And it's yet to be determined, but it will probably be the stud2 namespace. No. All right. Well, thank you very much for coming.